Welcome everyone. So today Abhishek will continue to talk about Riemann surfaces. We'll pick up from his last talk. You can start Abhishek now.
Okay, thank you, Abhay. Okay, so in this talk, basically we are going to talk about uniformization, representation, and classification of Riemann surfaces. First, I will mention the uniformization result, but before that, I must mention about lifted and projected complex structure. So we'll start with that one. Okay, so remember that. Okay, so R R be a Riemann surface. In short, I will write as RS. So a Riemann surface is a surface with a conformal complex structure. Okay, sigma. So remember that the surface S is nothing but connected Hausdorff topological space, which is locally Euclidean, R2. Okay. S be a Riemann surface, and E be a covering surface of R. Okay, so in the last lecture, it was an exercise that if you have a surface, its covering the space is again a surface. Means you can again define the local coordinate using the charts. Okay. So here is the first theorem.
So here P is
Yeah.
just locally homeomorphism or it will satisfy condition A also.
Yeah, condition A. Condition
Okay.
A. As I said that, yeah, henceforth we uh, will assume that covering surface, covering maps satisfies condition A. So that will be our definition now.
Okay.
So, R tilde carries a unique complex structure such that the covering map is such that R to R is basically holomorphic. Okay. Moreover, in fact, it is once you show it is holomorphic, it will be basically locally biholomorphic. Yes. Okay. So basically, what we will do. So let's see the proof of this one. So say this is your R tilde and this is R. This is our covering map P. So take a point x tilde belongs to R tilde and choose an open set u tilde, so that x tilde is contained in that one, such that p restricted to u tilde is a homeomorphism. And this we can always do. Any question? So this is your x tilde, and let us say this is our tilde. Okay, so this will be somewhere x, and we will get so yeah, we'll see that one. This is a homeomorphism. Now, since so what we are doing is take a chart. So we take a chart which is b comma phi. Okay, take a chart comma phi such that, okay, so this chart we are taking in R. Such that P such that this pair P restricted over U tilde, its inverse image of U intersection P phi composition P, okay, is a chart at X. Okay, so okay, so this is U, P of U tilde. Now again, this is our point X tilde, let us say. So again, we can take a chart. Let us say this is B. Let us say this is B, and this part is B intersection U. Okay. This red part is B intersection U. Okay. So again, R is a surface. We can again take a chart around this point X, and I am taking that chart as V comma phi. Okay. So what does it mean? Basically, phi of V is is homeomorphic to an open set in C. Okay, so phi of V is in complex plane C. Okay. So using this one, we are defining the chart at X. Sorry, at X tilde. Okay. Is it clear?
Yeah.
So basically, what we are doing is we are just pulling back the charts from below. Okay. Now we need to check the compatibility. So if we another chart, let us say B dash comma phi dash at. Just remember that up to this point, I have not used anything. I have not used the complex structure of R. Okay, at X, then the and the transition map for the pair. So the pair is P restricted over U tilde inverse series of V intersection U, phi composition P. This is our first pair. And so see, if you choose a chart V comma phi, you will get a chart uh, in X in R tilde around X tilde. If you choose another chart, you will get another chart at X tilde. Okay? This pair. Inverse series. So inverse series of V intersection U under the function, which is nothing but the restriction of P over U tilde. P, okay, is phi composition P, phi dash composition P. Sorry, here it should be phi dash. This should be V dash. Phi dash composition P inverse is nothing but okay, which will be nothing but phi composition phi dash inverse. Okay, so now now we have two charts in R tilde. Okay, first chart is this one. Sorry. Yeah, first chart is this one, and the second chart is this one. We need to check the compatibility of this one. Okay, so we need to check whether the transition map is holomorphic or not. Okay, so basically, once you check the transition map, we are getting this one. Okay. Now, what about this one? So they are
This is
basically the
holomorphic.
charts. Yeah. So they are basically the charts. Phi and phi dash are charts in the Riemann surface R. Okay. So basically, these are compatible. Phi and phi dash. So the transition map will this one will be compatible. This will be holomorphic. So this is holomorphic. Why? Since R is a Riemann surface. Okay. So now we have the compatible charts. We just collect these charts. Atlas. So remember that once you are defining a complex structure on a surface, it means that you have to define an atlas, because every atlas will be contained in a unique maximal atlas. So that will give a complex structure. Okay. This atlas phi composition, this map P. What is this map? So this is basically the restriction for this set. Okay. Still they belong to X. No. So this will be atlas because charts are compatible. So this defines a complex structure R tilde. Okay, so hence R tilde is Riemann surface. Up to this it is clear?
Yeah.
Okay. So now what else? So we have given a complex structure. Now we have to show that in this complex structure, the covering map is holomorphic. And then we need to show that show the uniqueness. Okay. So with this Riemann surface structure, function P such that R tilde to R. Okay, so basically what we're doing, so here is X tilde, we have this U tilde, okay. So this U tilde under P, we are getting this U, okay, at the point X, which is nothing but P of X tilde, okay. We have chosen a chart at X, which is V. So this is V, and this red part is V intersection U. Okay. Now what we are doing is we are taking the inverse image of this V intersection U under the map P restricted over U tilde. So, and that will come as, let us say, this one. That will contain X, obviously. Sorry, that will contain X tilde. So what is this? This set is nothing but inverse image of the intersection U under the map, this one. Okay, fine. Here we have phi composition P, which will map this one to phi of the intersection U. Okay. So to show that this function, so basically this function P is a map between Riemann surface. Okay, P says the R tilde to R. So just recall the definition of holomorphic functions on Riemann surface. Basically, they have to be holomorphic via charts. Okay, so what are those charts? So basically, let's see that. So P is holomorphic if and only if phi composition P inverse is holomorphic. But this one is clear.
Okay, so the R tilde has a atlas, say, map phi compose P, and you are
Yeah. So
showing P is a holomorphic, and there is a one more phi. Yeah, correct. So there should be.
yeah. So this should be holomorphic, isn't
Correct.
it?
Yeah. Mhm.
Yeah. And this is basically the identity map. So it is holomorphic. So with this Riemann surface structure, our map P is holomorphic. So basically, this is again your phi P intersection U and phi. This is nothing but phi composition P, composition phi composition P inverse, which is nothing but the identity. Okay. So this is just by the definition of holomorphicity. So I hope it is clear now.
Yep.
Yeah, so now we have seen that uh, we have seen a complex structure on the covering surface such that the covering map is holomorphic. And this is basically the unique complex structure. So we will talk about the uniqueness. So regarding uniqueness, so just bear with this notations. Okay. Let R tilde RS be another Riemann surface structure on R tilde such that the map, this covering map, P such that R tilde to R is holomorphic. Okay. So what do we need to do is that this basically we need to show that these two complex structures are seen. So this is any arbitrary Riemann surface structure on R tilde. Okay. So there is one observation. Okay. So let X be a Riemann surface. A chart P comma phi is in the Riemann surface is in the Riemann surface structure. Okay. So basically, this chart belongs to the maximal chart. This chart belongs to the maximal atlas, which contains all the charts compatible to this chart V comma phi. Is it clear? Write it down. That is, it belongs to the maximal atlas that contains all chart compatible to the chart V comma phi. Okay. So let X be a Riemann surface. A chart is in the Riemann surface structure if and only if this map phi such that V to phi of P. So this is basically open subset C. This map is holomorphic. Whether the statement is clear?
Yep.
So one part is like easy one. Which part is the easy one? See the proof of the observation. It's a small proof, but I will just mention.
And the forward one is easy.
Yeah, to show that it is holomorphic if it is in the maximal atlas. This is what you mean, Ravi?
Yep. Yeah.
Okay. So conversely, suppose phi says that V to phi of V is holomorphic. Now, what do we need to show? We need to show that so that p comma phi, this chart is compatible with every chart. Let us say p dash comma phi dash in the maximal Adler for x.
Now phi is holomorphic, so we know that phi compose phi inverse is also holomorphic. Phi prime inverse is
Yeah,
also holomorphic.
that's what. Yeah, that's what.
Okay.
Yeah, so it's easy. I just wanted to mention it. Okay, so anyhow, he got the point. So basically, phi dash composition, phi inverse is holomorphic. Okay, since we assume that phi is holomorphic. Okay, so this is clear. So basically, they are compatible. Now the thing is, okay. So now we can move on the proof of this one. So if w tilde comma phi tilde be a chart in the atlas for this Riemann surface, okay, then by observation phi tilde w tilde to phi w tilde is holomorphic, okay, and now what this will imply,
Is W tilde this chart will contain in a maximal atlas
for
for the whatever you define the P inverse or P compose phi inverse one or P inverse compose phi one or
okay,
something.
means maximum address for the Riemann surface R tilde,
Yeah.
isn't it? Yeah. So this is holomorphic, and this will again imply by observation that W I tilde is in the atlas for R tilde. Okay. So I think now the uniqueness is done. Is it clear? So basically, we have taken the chart in this Riemann surface structure, and we have shown that this will again belong to this R tilde. Again, you can do the converse part also in the same way because of this observation. So, is it clear?
Yeah.
So basically, the conclusion is covering surface of Riemann surface is always regarded as the Riemann surface with the lifted complex structure. So I hope it is clear. Okay. So once you have a Riemann surface, its covering surface is again a Riemann surface, and there is a unique complex structure so that the covering map will be holomorphic. Now the same thing can be done that we'll call as projected complex structure. Okay. So again, let R be a Riemann surface and G be a properly sorry so G being properly discontinuous and free group of conformal self map. So here by a conformal I mean that it is holomorphic 1-1 and onto map. Basically that is a biholomorphism. That is what I mean by conformal map. Conformal self map of R. And he says that this will be the canonical projection. GB projection. Okay. So then the surface. So again recall that since G is acting on R properly discontinuous and freely, so this R by G will have a surface structure. Okay. So then the surface R by G carries surface R by G carries a unique complex structure which lifts to the original complex structure of R. Whether this statement is clear?
Yep.
So again, like if one wants to check this one can, okay, yeah. So one has to be careful by defining the coordinates on this surface. But once it is done, it will be in the similar way of the lifted complex structure. Okay. So that was basically in the exercise to show that it is a surface. So if one can show that it is a surface using this property, then it is easy to like grasp this one that it has a unique complex structure, which is nothing but the lift of original complex structure of R. So now we'll talk about, okay, yeah, one more thing. Let me just recall. Okay, yeah, so here's one thing. I think nobody asked me this thing. So in the proof of this one, uh, I'm taking the universal covering space of a surface S, uh, and then we are showing that G is transitive, the covering group is transitive. And here, uh, 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 I'm taking a point x tilde, and we are joining x1 tilde to x tilde by a curve gamma. Okay, and we will. I will repeat this proof, like idea of the proof in some of the other theorems also. But so, what is the guarantee that such curve will exist? Can anyone tell me?
Is it a connected open set? So this is path connected. No. Or it may not be open. Or
Yeah, yeah, but the idea would be that one only. But yeah, it is not
uh,
open. Yeah. So basically, keep this in mind. I'm saying this because once I will talk about this fundamental group, there I will mention. So a connected manifold will be path connected. Just one just need to use the locally Euclidean property. Okay.
okay.
Yeah. This is an important thing to note down. So we will now move towards the uniformization theorem. So obviously, I'm just going to state the theorem. So every simply connected Riemann surface R is conformally equivalent to exactly one of the following. First one is the unit disk. Second, the complex plane. Third one is the Riemann sphere or extended complex plane. Sphere. Okay. Yeah, I will. I should provide a reference. So there's a research monograph like on the history of this one and the work of Poincare and Kobe regarding the proof of this uniformization theorem. Of Riemann surfaces. Okay, so one can go through this one.
Conformal equivalent means biholomorphic, right? I think
Yeah,
you said
exactly.
earlier. Oh, okay.
Mhm. Okay, so now we'll just use this uniformization theorem for our representation of Riemann surfaces. See this, okay, I will tell this one later. So let R be an arbitrary Riemann surface. Okay, so remember that in the previous class I told that every surface has a universal covering surface. Okay, universal covering surface means a covering surface which is simply connected. Okay, and any other two, any other simply connected covering surface, they are basically uh, homeomorphic. Okay, so let R be an arbitrary Riemann surface, and P comma R tilde be its universal covering surface. Okay, so since R tilde is okay, yeah, one more thing. See here, all these things are like R tilde. They are basically topological spaces. Okay, and the property of simply connectedness for topological spaces is defined by the a trivial fundamental group. So maybe I will cover that thing later, but keep that thing in mind. R tilde is simply connected by uniformization theorem. We have only three choices. Okay, so basically your R tilde is either normally equivalent to D, C, or C hat. Okay, so now it is better to work with only these three things: the unit disk, the complex plane, and the extended complex plane. Okay, thus without loss of generality, we have this situation described by so P such that omega to R, where obviously P of omega is R, and omega is either the unit disk, the complex plane, or the extended complex plane. Okay. Now we will see an important result. So, given an arbitrary Riemann surface R and omega. So omega always denotes either D, C, or C. Extended complex planes. Yeah. And omega, it's universal covering. Okay. Consider this group G. G belongs to the automorphism of omega. So automorphism means conformal self-map of this omega, means conformal self-map of unit disk, complex plane, and the extended complex plane. Okay, such that this P composition G is basically P. So obviously this is nothing but the covering group. Then this arbitrary Riemann surface R is conformally equivalent to the Riemann surface omega modulo G. Okay, so this is quite important. So this arbitrary Riemann surface is basically conformally equivalent. Is this statement clear?
Yeah, I think same you proved in a last lecture.
Yeah,
They are
exactly. That's what I said.
homeomorphic.
So yeah, homeomorphism. So up to that, we don't need to do anything because we have already proved that it is a homeomorphism. Like the desired conformal map will be that homeomorphism only. I will just mention the proof. So since omega is simply connected, okay, since omega is simply connected, so by this one, so by this theorem B, G is transitive. Okay, so omega is simply connected by theorem B, G is transitive. Okay, and hence by theorem A, this one, if G is transitive, then X tilde modulo G is homeomorphic to S. By theorem A, the map, so this is the natural map, phi such that R defined by phi of this class goes to P of X is this. Now, how to show that it is conformal?
Since P is holomorphic,
Yeah, exactly. I mean, the idea is same. So basically, it is conformal because the complex structure of R can also be obtained by projection from omega. Is it clear? Like the projected complex structure.
Yeah.
Is normal since the yes, structure of R is also okay. So this is the important thing. This is the representation of Riemann surfaces. Now the question is, uh, given an arbitrary Riemann surface, how to find it out the universe? What would be the universal cover? Whether it is unit disk or the complex plane or the extended complex plane. Okay, so that would come under the classification of Riemann surfaces.
What will be the explicit atlas for R minus G?
Sorry.
In the previous slide, so there is a sorry omega minus G. So how can we construct the explicit atlas or holomorphic atlas for omega minus G using R,
Okay.
right?
That you can
Means
do by
omega
the
minus
see wait that we can do by this one, by the lifted compressor structure. So that will be the covering of wait a minute. So basically omega is nothing but the unit is the complex plane and the extended complex
yeah.
plane. Okay, so that is a Riemann surface. Now
Mhm.
we are taking the cosine modulo G. So omega by G again has the Riemann surface structure coming from the Riemann surface structure of omega.
I see. Okay.
Yeah. Like projected conformance, I said, no? This one.
Actually, in this case, we are using properly discontinuous action of G on R to
Yeah,
define
that's what.
structure of this.
Yeah, that's what
Yeah,
I'm saying.
properly discontinuous action of G on R to define structure of the orbit space R modulo G.
Yeah.
Yeah.
I see. Okay.
So basically, if you remember that, yeah. So suppose X is a surface, is X modulo G is always a surface? That was the question. Basically, we can construct such examples where it is
I
not
see.
even
I see.
housed out.
Okay. So this is exercise. Okay.
Yeah. So we want some condition on this G so that X modulo G is again a surface.
Yeah.
That condition is G is properly discontinuous and freely. Once
Okay.
we have this condition, X by Z is going to be your surface.
Perfect.
So,
With
yeah.
some chart. Okay.
Yeah. So how to define the chart? There we have to use the properly discontinuous property of G.
I see.
Basically, yeah.
Okay. Thank you.
So the first theorem will be the only Riemann surface covered by this is again conformally equivalent to C hat. So basically they are, so in this conformal equivalence class, we have only C hat. So let R be a Riemann surface covered by C hat, and consider the group covering group. This covering group sometimes also called as deck transformation group. Consider the covering group G. G is nothing but G belongs to this automorphism of C hat such that P composition G is equals to P. Yeah, so here it is the main thing. So each element in G has a fixed point, isn't it? Is this clear? So basically, they are coming from the automorphism of C hat.
They are
Either it
Mobius
has
map.
one or two
Okay,
fixed points.
is it?
Yeah. Now recall this property of covering group, that it is free group, means other than identity, it doesn't have any fixed point. Okay. So basically, it says that each element of G is identity. Okay, so which implies it is singleton set basically, which implies G is trivial, and hence, so this R is basically conformally equivalent to, by this theorem, some name anyway, R is conformally equivalent to G, and G is nothing but the identity, so it is basically C. Is it clear?
Yep.
So the only Riemann surface covered by C hat is C hat itself, up to the conformal equivalence. Okay, so in this line, I will mention two results, but the proof is very much algebraic and complicated, which we will do it later. But
Is it same for unit disk and complex
no,
plane?
that, that is what I'm going to mention.
Okay, so the main point is the automorphism of C hat has a one fixed point at least.
Yeah, exactly. And since the covering group cannot have fixed points, so it has to be identity only. So we don't
Yeah.
have any such thing.
Okay. But automorphism of C is AZ plus B. Okay, it may not be fixed point. Okay, yeah.
Yeah. The next theorem is, so okay, so like I will mention this theorem and I will talk about fundamental group after this one. So suppose the universal so let R be a Riemann surface and C be its universal cover. Then, so okay, so this thing. So this is the fundamental group of this space. Sorry, this Riemann surface R. So basically, I will talk about this one later. Just but I think everyone knows about this one, the fundamental group. So this basically has to be, again, I said this is quite algebraic. See this one later, proof. But just to mention this result because it is important. This has to be abelian, this fundamental group. And okay, so sometimes it is also anyway, I will mention that thing later. So it is abelian, and in fact, has to be isomorphic to either to one of the this group Z. Okay. So the first condition is, so first is if this fundamental group of R is basically isomorphic. So for this one, I mean this by isomorphism. If this is isomorphic to singleton 0, then basically R is nothing but conformally equivalent to the complex plane C. Okay, that is quite clear. This A part. If so, the reason to consider the fundamental group will be clear later. Okay? If this fundamental group is isomorphic to Z, then R is basically your C star. Okay, C point is group is isomorphic to Z, then your R is basically conformally equivalent to the complex torus. Okay. So again, this gives us that up to the conformal equivalence class, the universal cover, the Riemann surface having the universal cover as a complex plane are nothing but complex plane, punctured complex plane, and complex torus. Is it clear?
Yeah.
I hope the statement is clear. Yeah. Suppose the universal cover space of R is D. Okay, means now we are considering the Riemann surface whose universal cover is the unit disk. Okay, so here we have two cases. First one is if the fundamental group of R is abelian, then we have only two possibilities. First possibility is if again this fundamental group is trivial, then X is nothing but unit disk. Okay. So in the group sense, whenever I'm writing this notation, you understand it as isomorphism. And in the Riemann surface case, whenever I'm writing this one, you understood it as biholomorphism. Second thing is, if this is Z, then X is basically D star, which is nothing but D minus 0, or sorry, or R is the annulus. Where your R is in between 0, okay. B is, so in this case, it can be non-abelian. So with that one, we'll get the compact Riemann surfaces. Is not abelian. Abelian. Then R is R is basically biholomorphic, morphic to a Riemann surface structure on a G hole torus. So it is basically the so these are the cases.
So here G is a number of holes.
Yeah, number of holes in the torus. So as I mentioned, why we are even considering this fundamental group? Here is the result. Theorem is basically so let I will write in the surface case. So let S be a surface surface consider W comma P its universal covering surface, okay, and G be the covering group of W over S, okay. Then basically this G is nothing but isomorphic to the fundamental group of these surfaces. Group of. So now you can see why we are considering the fundamental group of S.
Yeah, I think that's why whenever this fundamental group is trivial, you will get the D or C star. Your universal cover, then you will get easily right. Means if pi
Yeah,
1s is just
exactly.
identity, I
Yeah.
yeah just identity.
So G will be the identity once it is
Yeah,
trivial.
correct.
Okay, yeah, so there is one more thing. Okay, so let me just mention a idea of the proof, because again it is again algebraic. Because there's two way to understand this one. First, to understand how to prove how to prove okay, so how to prove the following statement, that every surface S has a universal covering surface. Okay, so that is another one, and I will write this one. So basically, let X belongs to W and gamma be a closed curve in S. Um, Px is equals to A. Okay. So basically, uh, here is a W. Just say this is our S. This is P. We have X. Okay. And here we have point A, which is nothing but P of X, and we will consider a loop, closed curve. This is gamma. Okay. Now again, the same technique. Let gamma dash be the lift of gamma from X. So let us say this is the lift. Okay, and Y belongs to W, be the terminal point of gamma tilde. Okay, so this is your Y. So since okay, yeah, so observe that basically P of X is nothing but P of Y, which is A. Okay, since G is transitive, there exists G gamma. Again, yeah. So this has to be unique. That will follow from an argument such that G of gamma of X is equals to 1. So now we have the idea to define the map. How to define the map? So define
G of gamma x equal to G of gamma y maybe. Uh,
no, this is fine.
okay.
Wait. Yeah. So basically, G gamma belongs to this group G.
Okay. Yeah. Okay. Yeah. Fine.
So this is a function. Define a map. This is that it's fundamental group of S to G by phi of gamma G of. So basically, this will be our desired map. So, isomorphism. Okay, so I will end it here.
And why is it unique? Is it easy to see or there is some deeper argument?
Okay, so That's what I said. Uh,
Mhm.
the way we define this. Okay, no, sorry. That is easy, kind of. So since G is transitive, uh, yeah. So basically, they will belong the same homotopic class. Okay? That's what I mean by unique.
It's-
Yeah, basically they will be
Okay, I
the
see.
homotopic. So that whenever you take a curve sigma in this one, this homotopic
Uh-huh.
class, this
Then by
whatever the 3
monodromy
sigma you get,
theorem.
that will be homotopic to that in that sense.
Yeah, maybe by monodromy theorem.
Yeah, because we have the lifting.
Yeah. So then this G gamma should be the class of G gamma if we define this phi, right? Uh, because this phi then is not well defined. How is defined right now? Means if you are saying it's not unique.
No, I'm not. Okay, wait. So this is basically a unique,
Uh, okay, I see.
and
Okay.
this
It's
will
simply
come as
connected.
uh,
I think because the W is simply connected, so that's why there is just one element on on that homotopy class. Maybe I don't know.
no, homotopic class will come once we saw that G is well defined.
Okay.
Philosophically, the way we have defined this phi, this has
Mm-hmm.
to be a single function, not the homotopic class,
I
because
see.
this is not a homotopic class.
Correct. Yeah.
So, so I think direct transformation argument is there. I have to see again.
Uh, yeah. So, so other than
Yeah,
that, I have
Abhishek,
one
yeah.
more little doubt in I think maybe second page or third page where you prove phi is holomorphic if and only if it is in some maximum atlas.
Yeah, this one. Observation.
Yes. So here you are saying phi is holomorphic from V to phi V.
Yeah.
So so in which chart? Means for any chart or there is a some chart? Because B is a some Riemann surface.
V is a open set in X.
Ah, so B is a some Riemann surface means.
Yeah. So
So
again,
it should
yeah.
so means it is holomorphic. So we define holomorphic with respect to some given chart, right?
Yeah. The thing is, once you have a Riemann surface, if you
Uh-huh,
take any open subset that has a
uh-huh.
natural Riemann surface structure by taking the identity map.
Correct. Yeah. Or by taking the restriction of the
Yeah, restriction of the.
atlas. Yeah. Yeah. So if this phi has a restriction of the this v comma phi atlas means the actual atlas or some other atlas means I'm saying we have a Riemann surface there is a some atlas so now
Yeah.
you're defining this phi from v to phi v so this
Uh-huh.
phi has a or this v has a atlas which is restriction of the given atlas of x or some different atlas.
No, yeah. So this the Riemann surface structure of V means the atlas
Uh-huh.
of this V coming from the Riemann surface structure of X
Okay.
means by
Yeah,
taking the restriction of that one. I mean, you can just
correct.
take the
So
V
here,
intersection that atlas,
correct. So here
that
the
chart.
correct. So here there is a no two atlas means we have a given Riemann surface. It has a some
Mhm.
atlas, and we are just restricting to that atlas.
Exactly.
Right. Okay. But now you prove the using this observation something that there you have a two atlas. There is a some R tilde
Yeah.
RS and one R tilde.
Yeah, so now
So
we are
here,
basically, this is just an observation for any arbitrary Riemann surface.
okay, yeah,
Okay. Now we are
mhm,
proving the uniqueness on this
okay,
R tilde. So
correct.
we have already defined a Riemann surface structure on this R tilde
Correct.
by the lifted
Using
complex
correct
structure.
P. Yeah.
Okay. Now we are assuming that, let us suppose there exists another Riemann surface structure, and let us
Mhm,
denote it by R tilde RS.
yeah.
Take a chart in that one.
Okay.
Okay. Now consider this Riemann surface structure, and we have
Mhm,
taken this chart. Okay. By the
okay.
observation, this will be holomorphic.
Correct. Yeah.
Okay.
With
Now
respect to
if,
the new chart. Yeah.
yeah, so now if this is holomorphic,
Uh-huh.
this is again will, so this will, again, this is if and only if. Okay. This observation, this is if and
Uh-huh.
only if. So now
Yeah.
if this is
Correct.
holomorphic, so this will go into the Riemann surface structure, means in the maximal atlas. So
Correct.
W tilde and phi tilde will be in the atlas for R tilde also.
Yeah. Okay. That's some. So here, you
So here
first
is your
define.
problem.
Yeah. Yeah. So means we changing the atlas. So that's little bit the problem for me because in our observation both
Well,
atlas are same up to say restriction. Okay, do you get my point? Means, or what I have doubt.
okay,
Means
so
I'm saying
basically you are
the
saying that,
observation is not same as this. Means, yeah. Means we can't exactly use this observation because in observation we just restricting our previous atlas.
so here this chart is in the Riemann surface structure
Yeah.
of basically X. This should be holomorphic. Here this chart is in the atlas for this Riemann surface structure.
Mhm.
Okay. By this one, we can say that this is holomorphic.
With
Okay.
respect to the new chart, new
The,
atlas.
the atlas in this one,
Yeah.
okay, wait a minute. So basically we need to show that this phi tilde is
Yeah.
holomorphic
It's with respect to
in
this
the
new with respect
in
to
the
the
Riemann surface structure
pullback.
of R
Yeah.
tilde.
Correct.
And R tilde atlas consists of this chart.
Yes.
So basically W tilde is nothing but this one, and phi tilde.
Yeah. I think
Abhishek,
usually we. Okay.
Okay.
Abhishek, you have 5 more minutes. Maybe you can try to wrap it.
Yeah. Just. Uh, okay, yeah, Ravi, that is a good point.
Or we can discuss later. Yeah.
Yeah, we can see this part.
Mhm. The update is New Zealand wins by 3-0.